everybody. Um, well, first of all, I'm sorry about the background noise. I think I have some problem with my computer. Actually, it's not a microphone or whatever. Okay, let's get started with this one. I want to talk about the design of a binary coder, and in the term of apply T flip-flop is a flip-flop, and also JK flip-flop. Um, let's get started with the truth table first. In case we have three inputs or three binary bits, ABC, and the next stage I represent by A plus, B plus, and C plus. And I also want to take a look at the input of the flip-flop in terms of flip-flop A, flip-flop B, and flip-flop C. Okay, let's take a look at what we're going to do now. The sequence of the flip-flop states that we want to decide is that we want to start count the number from 0 to 1 to 2 to 7 and then back to 0 and continue the process again. And you know that, for example, binary bits 110 that's represented by the base 10 or 6, right? And that's you can get it from what? Um, let's start from the last one. So you have 0 multiplied by 2 to the power 0, and then plus the 1 multiplied by 2 to the power of 1, and the last one is the 1 multiplied by 2 to the second. So that's give you 6, right? This one is give you 4, and this 2, and it's 0, and that's give you 6. So that's mean you want to for three binary bits, you have start from 0, 0, 0, 0, 1, and then you end up with 110 and start over again. That's going to be your 0, 0 again. So let's take a look at the truth table. You have the present state ABC. You have three binary bits, so the logic combinations, the total is going to be to the third. That's the 8 combinations. So you start from 0, 0, 0, 0 for A input and 1, 1, 1, 1. And for B is going to be what? 0, 0, 1, 1, 0, 0, 1, 1, and C is 0, 1, 0, 1. So the next stage, when you start counting from 0, 0, the next stage is going to be 0, 0, 1. So the next stage, after this one, is going to be what? 0, 0, 1. The same thing as for this stage, the next stage is going to be what? 1, 1, 0, right? Because this stage will follow 0, 0, 1. Okay, that's how you get the next stage through table. Now for the flip-flop input, we have TA, TB, TC. In this case, we use the T flip-flop, the simplest one. And whenever to create the flip-flop input, you can take a look at that the present state and the next stage. Whenever that you have the present state change to be the next stage, this means your T flip-flop the input have to be 1. Take a look at for C input. It's always change the state from 0 to 1, 1 to 0, 0 to 1. They all change. So that means your TC have to be 1, 1, and 1 all the way down here. For TB, take a look. For the first one, the present state is 0, and the next state is 0. So it doesn't change the state. So your TB still be your input of your T flip-flop is going to be 0. The second one, change the state from what? 0 to 1. So your TB have to be 1. Okay? So you probably get an idea, how to create the truth table for flip-flop input for TA, TB, TC. And for example, for A, for the last one, change the state, right? From present state 1 to be your next state 0. So that's the TA has to be 1. So when you already have a complete truth table for present state, next state, and flip-flop input TA, TB, TC, you have to move on to design the digital circuit for flip-flop input TA, TB, TC. Now you take a look at TC input. You see that your TC is always B1. So that means it will be connected to the pulse. Right, no doubt about that. Since pulse TC causes C to change state, the pulse source must be connected directly to C input at following. So this is the digital circuit for your TC flip-flop. Now for TB input, why is come up to be your to input AND gate? Well, you have to get back to the truth table of your input TB. What we see is that when the power is received only if C equal to 1. Okay. Or notice the present state turn out to be the next stage, and you have to design your input of TB according to the truth table. And let sorry, let's get back to the truth table again. I have, let's see, somewhere here. Okay, here. Let's take a look. So this is your TB. Have to follow the truth table 0 1 0 1 0 1 0 1. So when you have a two input AND gate, oops, sorry. Whenever C equal to 0, it gives you what? 0 and 1. The power is always 1, right? So 0 and 1 is going to give you TB to be 0. Whenever for the AND gate, whenever you have 0 show up, your output is going to be 0. So that's how you get your TB. You take a look at this one, 0, 0 1, and this is your TB. So it's follow what? Exactly follow C input, right? When C input is 1, your TA is 1. When C is 0, your TA input is going to be 0. So that's why we apply two inputs AND gate for TB input. Now it's work the same way, similar to TA. Okay, this is your TA. It means that this will follow the 3 input AND gate. When you have the input to be B from C and from pulse. You take a look at the truth table. So you still use the AND gate, right? But become a 3 input AND gate. And whenever you have a 0, so you focus only B and C and pulse. So whenever you have a 0, that means your TA is going to be 0. So let's say in this case, BC is 1 1. So that's why you have TA become 1. And also the last one here, you have our BC is the 1 1. So your TA is also 1. So that's why you end up with 3 inputs AND gate for TA input. Okay, to better understanding, you can also apply kernel map to create the digital circuit for T flip-flop input. This one I conclude inputs TA, TB, and TC. That's mean when the present state is different than the next state. or change the state. So your TC have to be 1, same as uh, TB, TB flip-flop, and also TA flip-flop. So you can make conclusion for C and C plus, present state and next stage. This is the 0011. So whenever the present state change the logic to the next stage, or it's not the same, so your TC have to be 1. Right? Or you can use the 3 input exclusive OR. Now let's take a look at the kernel map for input TC, TB, and TA. By follow your truth table, you can write down your TC. Since your TC is always 1, so that means your TC has to be connected to the power signal or the clock. And for the input TB, you can create the kernel map with the 3 inputs A, B, and C. So it has to be 0 and 1. B is 0, 0, 1, 1. C is 0, 1, 1, 0. According to the truth table, you can create the kernel map. And from this map, you can see that your TB is going to be C AND gate with pulse. Okay, you get C because you take a look from the left to the right of the rectangular, the red pens, the red color here. A changed the state from 0 and 1, so we ignore A. And for from the top to the bottom here, B also changed from 0 to 1, so we ignore B. So what left over is C. That's why we have C here. Okay. Do the same for TA. So your TA is what? You have for A, change the state from 0 to 1, from left to right. So you ignore A. And for B and C, it doesn't change the state. So you have to take B as B and C that's 1. It takes this one as C. So your TA is equal to BCP, or 3 input AND gate with the input of B, C, and pulse. Okay, so finally you will have your circuit as in this picture here. So you have TA, TB, TC, and that's going to be your ABC, be a counter output for the present state and next stage. Let's move on. Even have example with straight binary order. That means I don't need to count, from 0 to 1 to 2 to 3, but I have a state diagram here like this. So that's one. If you start, the state 0, 0, 0, and then the next state is going to be 1, 0, 0. And if you start from the present state 0, 1, 0, the next state is going to be 0, 1, 1. So you have a truth table for 3 inputs A, B, C. Do that's the same as what I mentioned above. And okay, your job has to create truth table according to the state graph. Let's take a look for just example. For the present state 0, 0, your next state is going to be 1, 0, 0. That's why I have 1, 0, 0 here. And for the state 0, 0, 1, you don't have the state, present state 0, 0, 1 here. So you don't know where to go. We put it the don't care state. So you can work out for the rest. And this one, the present state 1, 1, 1. The next state is going to be 0, 1, 0. So that's why I have the next stage to be 0, 1, 0 as in the truth table right here. Okay, so now you probably get to the point. And then the next step, we going to do the complete truth table That means include TA, TB, and TC. Okay, you do the same thing. So you write down the present state and the next state, according to the state graph above. Um, let's take a look at TA first. Here, the present state is 0 for A, and the next state is 1, or A plus. So that means A change the state from 0 to 1. So your TA has to be 1. Whenever it doesn't change the state, for example, this one, A, present state is 0, and the next state is the 0, still the same. So your TA has to be 0. And if you don't have a don't care state, just put don't care state, in there for TATBTC. So that's all you have. And the rest you can work out by yourself. The next step is to create the Kano map, just like this. Okay, so that's pretty much about how to decide the counter, binary counter, or digital circuit. And now it's going to be a little bit complicated for let's move on to counter design using SR flip-flop. First of all, you need to take a look at the behavior of SR flip-flop. So I put down here as the input is RQ. Q is the present state, and Q plus is the next stage. So you have 8 combinations, right? And then what I have, here, I make a summation, right, from table A. So that means I pick up Q and Q plus. That means the present state and the next stage. So you have 4 combinations, 0, 0, 1, 1, 0, 1, 0, 1. And for 0, 1, you can see that, Q, this is 0, 0, right? 0, 0. I'll pick up this one. And you also have 0, 0 for Q and Q plus. That's all you have. So that's the includer SR 0, 0, and 0, 1. That's why I have 0, 0, and 0, 1 here. For Q plus, is there 0, 1? Where is 0, 1? Here. You have only SR to be 1, 0. So you have only SR. Only one state here. And the same thing as 1, 0. Right? Where is 1, 0? Here. See, SR become a 0, 1. So that have you 0, 1 here. But for 1, 1, here, Q plus, you have 2 states of our SR. That means 0, 0 and 1, 0. So that's why I have 0, 0 and 1, 0 here. And you can make conclusion, summarize to the table C. So this one, since the S doesn't change for Q plus state is 0, 0. So S still maintained to be 0. But R, changing from 0 to 1, or it can be either 0 or 1. So I put this one at X or don't care state. Same as Q plus 1, 1. R is still same to be 0. So you keep R as 0, and then there is, don't care state, because it can be either 0 or 1 to create 1 and 1 for Q plus. Okay, so that's for the SR flip-flop. And you're probably familiar with what they say, like Q plus is equals to 0, 1. So you take a look at the Q plus 1. So that's mean you set the flip-flop to 1, or the output or the next stage to be 1. So your SR is the 1, 0. And for Q plus equal to 1, 0. So you take a look at this one, 0. So that means you reset the flip-flop to be 0. 0 and 0. And your SR to be 0, 1, because R equal to 1. And for Q plus equal to 0, that's the according to S equal to 0, R equal to X, or don't care state. That means preventing flip-flop is set, Q plus to be 1. That's opposite the case number 1, because you want to set the next state here to be 1. So your SR going to be 0x. And for QQ plus is 1, 1. Okay, you want prevent setting flip-flop, resetting. Resetting is mean you don't want the next stage to be 0. So you want to maintain the logic of Q plus to be 1. So that's mean S equal to don't care state and R equal to 0. So that become X0. Okay, now we work out on the counters. Refer to the truth table of the counter, above that we have. So let's take a look at the state ABC equal to 0, 0, 0. And that we know the next state is what? 1, 0, 0, right? According to the state graph. And then you that's mean your AA plus is the state 0, 1. So you refer to this there is our flip-flop. This mean QQ plus is 0, 1. So you pick up this. So SR state is going to be 1, 0 here. And that's why you have 1, 0 for SA, RA. So this one I work out only for SR flip-flop A. Okay, and you can work out for the rest for B flip-flop and C flip-flop. For ABC equal to 0, 1, 0. And the next state is what? 0, 1, 1. So your A plus is the 0 and 0. Then you pick up this one. SR equal to 0 and don't care state. Alright? So that's very clear. Now let's summarize the truth table. You can work out this by yourself. So that's the truth table, complete truth table for the 3 input binary ABC and the next state, and also the input for is a flip-flop of A, B, and C. Okay, you can work out for the same thing for the Kano map for SR flip-flop, and that's the complete logic diagram for binary counter. That's referred to the state graph. Okay, you have 2 input AND gate. That means one input is come from pulse or clock, and for A, you take one input from C. RB, one input from C. Now let's move on. So that's what you need to know is the behavior of SR flip-flop or the truth table. That's gonna help you a lot. Same as JK flip-flop. That you need to start with the truth table of JK flip-flop. You have JK and Q. So you have A combinations, and Q plus is going to look like this. And you can draw, you can summarize, the other table using Q plus for JK. You do the same thing for Q plus is 0 here, 0. You have 0 here, as well. So is come from JK equal to 0, 0, and 0, 1. So you have 0, 0, and 0, 1. And this turned out to be your what? J still doesn't change the state, so you keep 0 here. And K is what? Change from 0 to 1, so you can put like don't care state for K. And for 1, 1, you have K doesn't change, so you put 0 here, and J, change from 0 to 1, so you put the don't care state. And finally, you can do work this out by yourself. And this is complete truth table for the JK flip-flop as the counter. Okay, so that's how I want to mention about just review for the binary counter digital circuit for binary counter. Okay, I'll see you later. Bye.